Thank you very much. Good afternoon, ladies and gentlemen. I'm from Elgin Fruit Juices. We're a company based in Grabouw in the Western Cape. I'd like to take you through the journey we have with the NCPC, which was a very profitable one for us, which helped us reduce our water use in the factory tremendously. And although we're in the Western Cape and we all know about the problems that Cape Town went through, there's a little story I'd like to share with you that maybe not all of you knows. But Grabouw is only 80 kilometers from Cape Town up in the mountains. And we are probably one of the highest rainfall areas in South Africa. So we get between 1,200 and 1,400 millimeters per year. We never had a water problem, never. We are actually the reason why Cape Town didn't reach day zero. Just when Cape Town had about 15 days of water left in the system, we released from our dam in Grabouw, the Eikenhof Dam, we released, I think, 10 million cubic meters of water that went over the mountain to Cape Town, and that was one of the reasons why they avoided day zero. I wouldn't say the only one, but it was one of the reasons. So you might thought, so why is a company that's sitting in this area looking to be water efficient? And I'll try and explain it a little bit more. So Elgin Fruit Juices is a company that's a wholly owned subsidiary of the 2A Group. And our shareholders are 55 apple and pear farmers who farms in the Elgin, Grabouw, Fairbairn, Villiersdorp area. And Villiersdorp had a massive water issue. The Theewaterskloof Dam, as you all know, I think turned at about 10% water in the dam. So our fruit that we use in our factory comes from this area. So we cannot stand idle in terms of water use, even though in our specific area we have enough water. So to be a shareholder of 2A, it's only current producers of fruit that can be shareholders of 2A. So it basically worked like a cooperative, even though we are now a company. And our shareholders farms about 2,500 hectares of apples and about 500 hectares of pears. So collectively, probably about 12 to 15% of the South African apple industry, and also in that region of the South African pear industry. And just to give you an idea, so our shareholders are sitting here at the top. Just want to see if so that's our shareholders, only farmers. They own the whole group, and the group has invested extensively into the value chain in the last 25 to 30 years. So there is Elgin Fruit Juices. So the 2A itself focused on production or packaging and distribution, cold storage of fresh apples and pears to the market, and packs about 7 to 8 million cartons for export and about 2 to 3 million cartons on the local market. We at Elgin Fruit Juices, we add value to the fruit that cannot be used on the fresh market, so anything with some blemishes on or something like that, we make concentrates from, apple juice concentrate and pear juice concentrate from. And then our marketing company is a joint venture with another similar size apple and pear company in the Western Cape, Ceres Fruit Growers. Through Cape Fruit Marketing, do all the marketing in I think on last count, 104 countries all over the world. APL Cartons is a manufacturer of corrugated cartons in the Western Cape, and that supplies all the corrugated cartons that we pack our fruit in. And then Link Supply Chain manage the whole logistical chain from our pack houses right all over the world to the DCs of the big supermarkets in the UK and things like that. There is another, in total there's now 32 companies in the group, all involved in the value chain, and all of these companies work on a cost basis, so everything that we make in profit is rebated back to the farmer to keep our farmers sustainable. That's a story for a different day. So the volumes we handle at Elgin Fruit Juices, roughly about 75,000 tons of apples and about 15,000 tons of pears every year. Of which 70% of this volume comes from our shareholders. In the group, we have a philosophy that we need to do outside business as well, just to keep ourselves honest and make sure that we are still competitive in the market. We produce about 9 million liters of apple juice concentrate, 70 bricks, and about 1.6 to 1.7 million liters of pear juice concentrate, also 70 bricks. Then one of the waste products is pomace. That's sold to the local dairy industry, about 12,000 tons. And then we also produce a little bit of apple aroma, which is sold to flavor houses all over the world. So our factory was quite old. It started in 1980, and then after I started in 2006 at this factory, we embarked on a massive capital expansion program just to catch up with technology. And we spent roughly about 105 million rand in the plant, which includes, among other things, a new in-feed line. We fully automated the process. Our process is now so automated that I can run it from a chair in Mauritius if I have a good internet connection. I haven't done it yet, but I'm hoping to do it sometime next season. We used big presses to press the juice out of the fruit. That got a control upgrade. We installed a second pressing line to increase the yields in the plant, ultrafiltration plants to remove solids from our product. And then what we also installed was a new absorber or resin columns. In the past, we used activated charcoal and gelatin to remove what's called patulin, which is a mycotoxin from our juices. Now we installed the absorber plant, which cut our production cost, our direct production cost, by about 25%. One issue that we had with the absorber plant, it uses a massive amount of water. Roughly about 750,000 liters of water is used per day for regeneration purposes. And then we also installed a massive evaporator. So we evaporate the juice or the water of the fruit juice so that we're left with basically a sugary syrup. And therefore we have an evaporator that can evaporate 70 tons an hour of water. But we had some problems, and mostly in terms of water. So all of a sudden, mostly because of the resin technology that we installed, the volume of wastewater generated in the plant started to put our effluent plant under pressure. Now in our case, our effluent plant is roughly about 5 kilometers from our site, so it's been piped to that effluent plant. And there's a finite capacity limit on what we can put through the pipeline, and we were very fast approaching that limit. And this is why a lot of our water investment made a lot of sense, because for us to actually go and increase the capacity of our pipeline up to our effluent plant and also increase our effluent plant would probably have cost us in the region of 25 to 30 million rand. We also found that out of our ultrafiltration plants, the COD values that comes out of there, that was also sent through to our effluent plant. The COD values coming out of ultrafiltration plants in the region of 70 to 80,000. So that was putting a lot of strain on our effluent plant. The water use in the factory was very high. Like I said, we were in the Western Cape, and we are in the Theewaterskloof municipality, and sort of in sympathy with Cape Town, we also went to level 5 water restrictions, although there wasn't any shortage of water. But in some of the other parts of Theewaterskloof, like the Villiersdorp area, there was definitely severe drought in that area. But the price of our water that we got from the municipality increased by about 400%. So we went from about 15 rand per cubic meter up to about 56 rand per cubic meter in one go without warning. Then at that stage we made contact with the National Cleaner Production Center through Green Cape, and they appointed a consultant, Darren Com, to do a water budget in our factory. And I'll share a little bit with it, and I'll get into a little bit of detail, so if you want to fall asleep, now's the time. So just to take you quickly through our process, so we start with what we call mash production. We take the apples or pears, we put them through a mill, make them very fine, add a little bit of enzymes, and we also add water. Then it goes through our presses, where we separate the solids from the juice, basically, into the raw juice tanks. From the raw juice tanks, we run it through a pasteurizer, which is actually the first stage of the evaporator, just to make sure that there's no fermentation in the factory. Then goes into deep-pec tanks, where we make sure that it's pectin negative and starch negative. Then it runs through the ultrafiltration plants, where we remove all the solids. It runs through the absorber plant, where we remove patulin and also make the color lighter of the product. then it goes into final tanks, and from there into the evaporator. When it goes into the evaporator, on that stage, it's roughly about between 16 and 18 bricks, and then we evaporate up to 70 bricks. And then we get out with final concentrate on the bottom line here. Now, we can do roughly about 1,000 tons a day can be our input here. So to give you an idea, when we run 1,000 tons a day, we get about 1,000 liters of raw juice from 1,000 tons of fruit. So that gives us 1 million liters of liquid that we run into the evaporator per day. And we make from 1,000 tons, we'll make roughly anything between 120 and 130,000 liters of concentrate, which means that we recover about 800,000 liters of water in the process. Now, just to give you an idea of how very inefficient we were, this is our total water use before we did any interventions. So all the processes is listed here, what we were doing in terms of flow rates, daily usage, and you can see there the absorber plant, top of the list, CIP of the absorber using 602,000 liters of water, and it comes down here to 51 million liters of water that we use on a monthly basis. Fortunately, we only run production for about 5.5 months of the year, so this is not 12 months, but for that 5.5 months, this used to be our figure. Just to put it for you in a little bit more understandable, you can see we saw the absorber was our absolute worst water user, and there we could see all the other water users down the line. And just to give you an idea of our cost of water, so like I said, in 2018, all of a sudden, our municipal water rate shot up from about 12 Rand a cube to 56 Rand a cube, and it actually went up to 58 at some point. So it was costing us for the year roughly about 5.1 million Rand we were spending on water, up from roughly about 700,000 to 800,000 the previous year. That was a bit of a shock in the system. So we looked at where could we possibly, and this all came out of the report from the NCPC, where could we possibly start looking at water savings, and we identified a couple of points. Reducing flow rates on the absorber, and that we did immediately. It didn't cost us any money, and it gave us a significant saving. We looked at CIP recovery, how we could recover all the CIP cleaning in place that we do in the factory, how we could recover all that water. We looked at some reuse opportunities, dry cleaning techniques, reverse osmosis. This was actually the only one of these 7 opportunities, and we actually identified a couple of other ones that we didn't introduce in at the end of 2018 for the 2019 season. And we also looked at caustic recovery, which for us was very interesting, and we are just about in the process now to commission this plant, where all the caustic that we use in the plant, we pipe that back to a tank, and then we run it through a caustic recovery plant where we actually clean the caustic and reuse it again. So this will cut our caustic bill, which is at the moment probably about the 3rd or 4th highest expense in the factory. We'll cut it by about 80 to 90%. So we went through a little bit of an exercise like this. We look at the different machines in the process, the evaporator, the 2 UF plants, and the absorber, and we say, right, when we go into a CIP process, we get out first the flush water, then the caustic, the spent caustic, and then the sanitizer. And what are we going to do with these streams? At the UF plant, basically the same. There we don't have a flush water, but we have caustic and sanitizer, but we also have in here the retentate that comes out there. And the absorber, we had the flush water, the caustic, and the sanitizer. So what we did is we installed, and because this is fully automated, it was quite easy to do with actuated valves and connectivity sensors in the line. So in the past, all this would go to drain. So now what we did is when the evaporator starts cleaning, and it cleans twice a day, when it's in that first step, this flush water will go to a tank, what we call our second pressing tank or sweet water tank. The caustic, after circulation with hot caustic, that will go to a recovered caustic tank, and the sanitizer water after that will go to what we call a sanitizer tank. The same with the 2 UF plants, and the same at the absorber plant. And also at the UF plant, our retentate go to a designated retentate tank, and then the pomace that we sell back to the dairy farmers, they were complaining it was too dry. So we started adding the retentate to the pomace, and we got rid of the retentate completely, and that 80,000 CODs is now eaten by dairy cows. The recovered caustic tank, we then run through our caustic recovery plant, recovering, well, the guys claim that we could recover anything between 85 and 90%. We'll see now. In my budget, I worked on 75%. So that's then recovered, the caustic's recovered, and then circulated back to the absorber plant to be reused there. The sanitizer water that we do is then a ring main through the factory with a pump running on a pressure switch, which is used for general cleaning. So instead of using municipal water or processed water to clean the floors and things like that, we were using the recovered sanitizer water there, and it's hydrogen peroxide. It lasts about 20 minutes in the water, then it's gone, so there's no risk to eyes or anything, so you can nicely spray it on the floor. It's very nice for general cleaning. And what we also did on the sanitizer water, we were using it in our in-feed in the flumes, because that water we also had to dump at least 4 times a day, and that dumping was about 40,000 liters every time we dump. So we're now using sanitizer water, reusing the water. And then, so let's just quickly look at all the machines. So at the evaporator, we had these streams. So the first flush water, which we're sending to the sweet water tank, the spent caustic, which we're sending to the caustic recovery, the rinse water after the sanitizer and the caustic, that we're still going to drain, because at this stage we're not planning to do too much with it. Sanitizer water went to the sanitizer tank. And then also at the evaporator, there's probably about 15 pumps running on an evaporator at the same time. And it all needs seal water, because this whole thing runs under a vacuum. So all that seal water, we run through a seal water recovery system, put it through a radiator to cool it down and recover that again. That's also saved us about 10 to 15,000 liters of water a day. At the UF plant, basically the same process, spent caustic to the caustic tank, rinse water to drain, sanitizer water to the sanitizer tank, and then also we were using the retentate to go to the pomace. Same with the absorber. Sorry about that. This was Bucher Unipectin was the company that we used to do most of the automation in the plant, and they were supplying most of the technology, but they didn't supply the absorber, so that's why it wasn't in the scope. Same story, flush water to the second pressing tank, and this water we were then using, because there was still about 2 to 3 bricks in this water. So we were not only recovering water, we were also recovering sugar. So that we sent back, and we use that when we do leaching on our presses, and so we were bringing that back in the pomace. Caustic to the caustic tank, rinse water to drain, and sanitizer to the sanitizer tank. Then also in the factory we had a big issue, because like I said, we were generating roughly about 700,000 to 800,000 liters of water a day, but there was a time lag. So every time we have to start up the factory, we didn't have water, and we have to bring in a massive amount of municipal water to start up. And then at some stage, once the factory is running for a couple of hours, then we have enough processed water, and we start this water is just then dumped on the floor or dumped down the drain, because we have too much. So what we did is we brought in a couple of extra tanks, and we started managing our tanks in the factory better. So we brought in a new 100,000 liter processed water tank. These 2 tanks was our initial. This is where all the water from the evaporator, the clear condensate and the raw condensate from the evaporator comes into these tanks, and also municipal water if the level falls too low here. From here it went to 2 tanks that we heat up to use for different processes in the factory and for cleaning. And then also to the absorber, which uses a lot of water, is supplied from these tanks. But when the evaporator has run for a couple of hours, what we found that this tank was starting to overflow, and this water was just going down the drain. So what we then did is we installed a process where the moment this level gets to 90% or so, the pumps would then open the valve and start pumping it into this tank. So that when we have to restart up after a while, then we still have 100,000 liter buffer capacity, and we can just run the water back from there to our processing tanks in order to ensure that we always use as less municipal water as possible. And then, so the extra water tanks that we installed was just the ones what we call our sweet water tank, second pressing tank, and here we supply it from the evaporator, from the absorber, and from the UF plants. We top it up with processed water if this level goes too low, and we heat this water up to 50 degrees because that's the temperature we need in the process, and then we supply. We use this water as a supply in the presses to leach so that we don't just dump it on the floor. The recovered caustic works basically on the same principle. It's supplied from the evaporator, the two UF plants and absorber, comes in here. It then goes through the recovered caustic system, and then from there it goes back to the absorber, replacing the caustic we normally used to buy for there. And the sanitizer tank, basically the same principle, except that we use the sanitizer tank to run a ring main through the factory for general cleaning, and also we go to the infeed line for our flumes, where the fruit, where we use that water then to wash the fruit again. And then our retentate tank is also supplied from the two UF plants. We actually now in a process where we can top it up with processed water if we want to, and then a flow meter in line, and we go to the pomace just discharge. So we discharge this retentate into the pomace, so we get our pomace now to a desired moisture content for the dairy farmers. So what have we learned? And so in the first season, without caustic recovery, we are only going to start now. We've already reduced our municipal water volumes by 20 to 30%. Actually, I think after caustic recovery, we will probably be at 70 to 80% reduction in municipal water use. Our effluent volumes have already reduced by 15%. Once caustic recovery comes in, it will reduce further, probably to by another 15 to 20%. All of a sudden, our COD levels in our wastewater treatment plant are under control and are manageable. The caustic recovery plant will be we're actually commissioning it this week. So I'm very excited about this. I think that will bring us lots of savings. And at the absorber, I think it's a technology for the future, definitely in our industry. But we still have to improve the water handling, and we're basically looking now to be exactly where we want to. So probably for us, the next step would be a borehole, and then treating that water, because water quality coming from the municipality can be a bit of an issue in our area. That's all I have.
Okay.